Hello dear students, a warm welcome to you all to the Power Hour NEET 2025 session. Today we will be having a revision of thermodynamics chapter. So let us see this important chapter. As you know, thermodynamics is all about study of different energies and their interconversion. So let us see a very interesting topic. So we will be covering here type of systems, work done in irreversible and reversible process, first law of thermodynamics, second law of thermodynamics. So let us start the first section, that is type of systems. So basically there are three type of systems. Three type of systems we are having. So let us have this as our universe. And in this we are having this system and surrounding. So this is our case 1 where we are talking about open system. Open system will be having, suppose one of the wall is not there and we are having open system over here. So in this we can see there will be both heat exchange as well as matter exchange. Case 2, closed system. In this we will be having same, we are having this our universe. System in this will be completely closed, so all the walls are there. You can see system and universe will be like system plus surrounding. So in this you can see there will be only heat exchange over here. There will be no matter exchange. And case number 3, that is our isolated system. In this we will be having same, this as universe, which is made up of system, and this time the system will be having insulation over here. You can see it is insulated. So insulator is used, which is a bad conductor of heat. This is insulation. So over here we will be having no heat exchange as well as no matter exchange, which is adiabatic process basically. So these are the three type of system over here. So we will be having the next subsection, that is work done calculations. Work done, and we are talking about work done by the gas. So let us see the work done. See dear students, there are two type of process, reversible and irreversible. First of all we will be talking about irreversible and then after reversible. But basically sometimes what happens, they are giving us an equation and they are asking us the work done. So for that must be knowing the basic definition of work done over here and how we derive the work done. So let us see the derivations. In physics we call work done as small work done as force into displacement, small displacement. This is for physics. Okay. For chemistry, the small work done, I am writing over here chemistry. For chemistry, the small work done will be minus force into displacement. For chemistry, we will be having this minus force into small displacement dx. So let us have this displacement. We are having this system, and here a movable piston is there. And suppose we are having expansion over here, expansion. You can see initially this length is x, cross section area is A, cross section area is equal to A, and we are having expansion over here. What will happen? Expansion, there will be small displacement by dx. So now the length is x plus dx. The cross section area is again A only. Cross section area is equal to A, but there is a displacement, small displacement dx. So over here, let us see the work done, small work done. According to chemistry, first of all, there the work done is minus force into displacement. But as you know, force is nothing but pressure into area. I am writing over here, force is nothing but pressure into area. So I can write it down, minus pressure into area into dx. Okay. We also know that the volume is equal to area into length. Differentiating both sides, we get dV is equal to A dx. So in case of this A dx, we can write down minus dV. So we are getting work done as minus P dV. For complete work done, we will integrate this complete work done, complete. We will be integrating this small work done minus, we are getting over here. Let us see what we are getting. Small work done integrated. We are getting minus integral P dV. So all over here, any case, if you calculate the work done, you should start from this formula. Work done is integral minus P dV. For all the work done that you are calculating, you must start from this work done formula minus integral P dV for chemistry. For physics, it will be integral P dV. Okay. So let us see how, which type of question we are talking about, that they are asking, where you must be knowing this derivation. So let us see this question. A sample of an ideal gas is expanded from 1 dm cube to 3 dm cube in a reversible process for which P is equal to K V power 3 with K is equal to 1 by 5. What is the work done by the gas? So again we are having this derivation already we done. Work done completely will be minus integral P dV. In this, put this P value as K V power 3. So we are having K V power 3 dV, and the K value they have given over here is 1 by 5. So I am taking this minus 1 by 5 outside. Integration of V cube dV, for the limits is from, we are having 1 to 2, 3. Okay. So let us have the integration over here. V cube integration is V power 4 upon 4, and the limits are 1, 2, 3. So we are getting minus 1 by 5 into V power 4. So 3 power 4 minus 3 power minus 1 power 4 upon 4 we are getting over here. So let us see the work done, what we are getting over here. Work done is minus 1 by 5 into 3 power 4 is 81, 81 minus 1 divided by 4. So we are getting minus 1 by 5 into, this is 80 by 4, 20. So this is minus 4 liter ATM we are getting over here. So our answer will be this first option, which is minus 4 liter ATM. So for this kind of question, you must be knowing that what is the derivation, what is the basic small work done, so that you can integrate it and get it the complete work done over here. And by this definition, you can also derive the work done for all the process. If by chance you forget any formula, you can derive it. Okay. So let us see the different type of process and their work done. First of all, I am talking about the irreversible process. We are talking about the irreversible process. How you will come to know whether it is a irreversible process or not? See, they must have written a statement over there. What is that important statement? Work done against a constant external pressure. If this statement is written over there, that means the process will be irreversible process. What statement? Statement, very important. You must see for this statement. Work done against a constant external pressure. If the statement you are looking, see, if they will try to uh, somewhat they will write down isothermal, adiabatic, they will confuse you. But you must be thinking, oh, so they have written adiabatic, isothermal. Important point is if they have written their statement, work done against a constant external pressure. That means it is a irreversible process, and over here we will see there is only one formula for this. It is adiabatic, isothermal, anything. For all, we will be having only one formula over here. Let us see what will be the formula. So statement work done against a constant external pressure. If you see this statement, it is a irreversible process. Okay. So let us see the work done derivation. Work done for irreversible process. Again, we will be starting from minus integral PdV. And here the pressure is equal to external pressure. We will be having P external over here. This P external is nothing but external pressure. And the volume is changing from V initial to V final. Okay. So let us have the derivation minus integral P external limits V initial to V final dV. So we will be having this is pressure is constant over here. So it will come out minus P external integration of dV V initial to V final. So this is nothing but minus P external V final minus V initial. We can write it down as delta V. So we are getting over here the work done formula. Work done for irreversible process is minus P external delta V. For any, whether it be adiabatic, isothermal, if they have written over here that it is work done against a constant external pressure, so the work done will be minus P external delta V. One more important point is about the units. Units you have to be very cautious over here. Units, if you want work done in Pascal into meter square, that we call it as Newton meter square. I'm writing a Newton meter square directly. So we are having, if you want work done to be in Newton meter, or you can read at joules directly. Joules, I'm writing out joules only directly. If you want the work done to be in joules, the pressure should be in Pascal, or you can call it as Newton per meter square, or and the volume should be in meter cube. So this is the work done. Units, if you want the work done to be in joules, pressure should be in Newton per meter square and volume should be in meter cube. Another unit that you must be importantly remembering, if work done you want in liter ATM, then the pressure should be in ATM and the volume should be in liters or dm cube. If you want the work done to be in liter bar, the pressure should be in bar and the volume should be in liters or dm cube. Important, one more conversion should be remembered, that the conversion is, by chance if they have given us the work done in liter ATM or you calculated it in liter ATM and you want it in joules, so you must be knowing the conversion that 1 liter ATM is equal to 101.325 joules and 1 liter bar is equal to 100 joules. How we got over here? See, 1 ATM is equal to 101.325 pascals. Okay, and the volume which we are having in liter, 1 liter is equal to 10 the power minus 3 meter cube. If you multiply, you can get the conversion over here. Same case over here, 1 bar is equal to 10000 Pascal, that is 10 the power 5 Pascal, and 1 liter is equal to 10 the power minus 3 meter cube. If you multiply, you can see you will get the conversion 1 liter bar is equal to 100 joules. So these are the important things. You must also remember the unit conversion. As you can see, they have asked question in NEET examination. So what question they asked in NEET examination? Let us see. Under isothermal condition, a gas at 300 Kelvin expands from 0.1 liter to 0.25 liter against a constant external pressure of 2 bar. Against a constant external pressure. So by looking at this, you must think this is a irreversible process, and the work done will be minus P external delta V. So let us see what will be the value. They have given the external pressure as minus 2 bar into change in volume. Final volume is 0.25 liter minus 0.1 liter. So we are getting minus 2 into 0.15 liter bar. So we are having minus 0.3 liter bar. Now I told you the conversion. Many times they are giving us the conversion value also, but we cannot say every time they will help us. So you must remember that 1 liter bar is 100 joules. So 0.3 into 100, we are getting minus 30 joules. So the answer we got over here is A option, minus 30 joules. So this is the question they ask in NEET examination. This is the PYQ question. You can get it over that they are asking many times questions from irreversible process. They have mentioned over here that isothermal condition. But as I told you, for irreversible process, always the work done is equal to minus P external delta V. Remember that they will try to confuse you, but you have to always remember this work done for irreversible process is minus P external delta V. So one more question we are looking over here. See, for this question, I am telling you, in first law of thermodynamics that we will be looking for, first law of thermodynamics. We study that energy can neither be created nor destroyed. It can be converted from one form to another form. And over here we see that the relation delta U is equal to Q plus work done. This relation we look over there, and in adiabatic process, as I told you, the isolated system, this is the isolated system we are using in adiabatic process. So the heat exchange Q will be equal to 0. So here delta U, which is the internal energy change, will be equal to the work done. And for irreversible process, this work done is minus P external delta V. So in this question which we'll be looking, which is the PYQ question, the delta U internal energy change will be equal to minus P external delta V. So let us see the question. A gas is allowed to expand in a well insulated container. So it is an insulated container, as I told you, this isolated system adiabatic process. And they have also said work done against a constant external pressure. So this is an irreversible process. So we are having this external pressure as 2.5 atm and initial volume is 2.5 liter, final volume is 4.5 liter. The change in internal energy delta U of the gas will be. So already told you, for adiabatic irreversible process, the internal energy change will be minus P external delta V. Over here, minus external pressure is 2.5 And the change in volume is, volume final is 4.5 minus volume initial is 2.5. So we are getting minus 2.5 into 2 minus 5, but the unit is liter ATM. So as I told you, delta U we have to calculate in joules, but we got in liter ATM. Told you that conversion is very important. You can see over here, they have not given us what is the conversion values. We must remember, we already studied that 1 liter ATM is equal to 101.325 joules, or approximately I am taking over here 101 joule for this question. So let us put the value minus 5 into 101 joules. We are getting minus 505 joules, minus 505 joules as our answer. So B option we are getting over here. So this is also PYQ question, previous year question they asked in NEET exam. So you can see how important is the conversion. So always remember the conversions as well. Okay, so this was all about the irreversible process that we studied. We saw the work done over here. So let us proceed to the reversible process. Work done in a reversible process. Let us see first isothermal reversible process. Isothermal reversible process. We know that isothermal, the word iso means same, thermal means temperature. So here the temperature is constant, temperature is not changing, temperature is constant over here, and it will follow the Boyle's law. PV is equal to nRT. You can see moles are constant, R is universal gas constant, and temperature is constant. So nRT is constant, PV is equal to K. This nRT is equal to a constant K. So PV is equal to K. This is nothing but Boyle's law, where we say P initial, V initial is equal to P final, V final. So we are having PV is equal to K. K is a constant equal to nRT. I already told you, always work done derivation will start from the formula minus integral P dV. So let us see how we will proceed. Here P is not constant. See, for integration along with dV there should be a term which is integrable. With dV we should have the V term. But here we are having pressure. So from here we can get pressure is equal to K by V. So put this pressure is equal to K by V in this integration of K by V dV. Minus K will come out, integration of dV by V. And everybody knows the integration of 1 upon x dx. Integration of 1 upon x dx is natural log of x plus c. So let us see what work done we are getting over here. Work done will be equal to minus K and integration of dV by V will be natural log of V, limits V initial to V final. So we are getting minus K ln of V final upon V initial. And the K value is equal to PV, or you can simply put nRT also. So we can have minus nRT ln V final upon V initial. I want in terms of log to the base 10. So we will be having minus 2.303 nRT log of V final upon V initial. So this is the work done we got in isothermal reversible process. What is the work done? Work done for reversible isothermal process is minus 2.303 nRT log of V final upon V initial. Of course, we can convert it into other forms also depending on the question. We can put that V final upon V initial is equal to P initial upon P final. If we are having the pressure values, not the volume values, you can have, instead of V final upon V initial, we can have P initial upon P final as well. Okay, so this is the isothermal process. Work done will be minus 2.303 nRT log of V final upon V initial. This is for reversible isothermal process. Okay, remember. So let us see what type of question they are asking. This is the question. 2 mole of an ideal gas at 27 degrees Celsius expands isothermally and reversibly from a volume of 4 liter to 40 liter. The work done in kilojoule by the gas is. So again, we already know work done, we already derived for a reversible isothermal minus 2.303 nRT log of V final upon V initial. Minus 2.303. Number of moles they have given 2 moles. And over here also you should remember that if you are asking the work done in joules, R value you have to take is 8.314, approximately 25 by 3. So the R value is 25 by 3. I am taking it approximately. Temperature 27 degrees Celsius, we have to take in Kelvin, 300 Kelvin. Log of volume finally is how much? 40 liter, and volume initial is 4. So we are getting over it as 10. Log of 10 is nothing but 1. So minus 2.303 into 2 into 25 by 3 into 300 into 1. So this is 300 times will be 100. So we are having minus 2.303 into, this will be 2500 over here into 2. 2500 into 2. So how much we are getting? Minus 2.303 into 5000. So we are getting minus 11480 approximately joules. Converted into kilojoule, divided by 1000, minus 11.48 kilojoule. This is the work done we are getting. So work done will be minus 11.48 kilojoule. So we calculated the work done for reversible isothermal process. So let us have a question over here where we will be having both reversible and irreversible process of the isothermal together, and they are asking us the work done. So this is the very important question which I am talking about. See over here you are having from this point to this point the work done is reversible, and from here we are having the work done as irreversible. Basically if you get a curve, that is the reversible, and we are having the blocks, that is irreversible. So they are asking us the complete work done during this process. So let us read the question. A 1 mole of ideal gas initially at 10 atm and 300 Kelvin is allowed to expand isothermally to 1 atm. Calculate the net work done by the system. In the PV diagram they have given all the data. Okay, so as I have told you, work done, they are asking us the complete, which is having two isothermal process. This is reversible isothermal and this is irreversible. So we will be adding up both work done reversible isothermal process and work done irreversible isothermal process. If we add both of them, we will get the complete work done. So let us see work done for reversible. We already studied minus 2.303 and RT log of See, over here they have given us the information that the pressure initial is 10 atm and the pressure final is 5 atm. So we will be having the formula minus 2.30 the nRT, P initial upon P final. P initial is 10 upon P final is 5. Plus work done for irreversible isothermal. Already we studied that it is always minus P external delta V. So we are getting minus 2.303. How many moles? We are having 1 mole. R value 25 by 3. Temperature 300. And log of 2. This is minus P external. See, in this irreversible process, this is our external pressure minus 1 atm. And V final minus V initial. See, PV is equal to nRT. So if we are not having the volume values, we can have V is equal to nRT by P. So over here, instead of V final, I am writing down nRT upon P final minus, instead of V initial, I am writing down nRT by P initial. So let us proceed further. This value you can see, this will be 100 times, this is 0.3, 0.3010 exactly, but I am taking approximately. So we are getting 2500 into 0.3, that is 750 into minus 2.303. 750 into minus 2.303 will be minus 1741 something. And here this value, let us calculate this value, minus 1 into nRT, 1 mole into R is 25 by 3 into temperature is 300 upon pressure final is, what is the pressure final value over here? 1 minus nRT again 25 by 3 into 300 divided by pressure initial was 5. So final step, how much we are getting in this 25 by 3, I am taking it as common into 300, and inside we are getting 1 minus 1 by 5. This is nothing but 4 by 5. This value is nothing but 4 by 5. I am taking it as 4 by 5. So how much we are getting? This is 100 times 100 into 4 by 5 into 25. This is 5 times. So 500 into 4 minus 2000 we are getting over here. How much we are getting? Minus 2000. So we are getting minus 2000 here, taking it upwards. We are getting minus 2000 this value, so I am taking over upward. We are not having that much space over there. Minus 1741, and this is minus 2000. So total we are getting minus 3741, approximately minus 3741 joules as our value. So B option will be the answer. So you saw that we are having both reversible and irreversible process over here. The curve one is the reversible and the block one is the irreversible. Okay, and we added up them and we got finally our complete work done, that is minus 3741. So second option will be the answer. Now let us proceed forward. We were talking about the isothermal process. Now let us talk about the adiabatic process. Adiabatic reversible process. Adiabatic reversible process. So already I told you that in adiabatic process we will be having an isolated system, that means heat exchange will be equal to 0. So Q is equal to 0 over here. Heat exchange is not there, and here we will be having the equation PV की power gamma is equal to constant. PV power gamma is equal to constant. This is the equation which will be followed here. So let us see the work done derivation, work done for adiabatic reversible process will be minus integral PdV. So let us see what is the P value. PV power gamma is equal to K. From here we can get the P value as P is equal to K upon V power gamma. So minus integral K by V power gamma dV. So let us integrate. Minus K will be coming outside. Integration of dV upon V power gamma. So what is the integration of this? It will be V power minus gamma plus 1 upon minus gamma plus 1. And limits V initial to V final. So this is the work done. Let us completely derive it. Work done for adiabatic reversible process. We are getting how much? Minus K into V final power minus gamma plus 1 minus V initial power minus gamma plus 1 upon minus gamma plus 1. Limits I already put inside. So let us take this minus inside. We are getting K into V final power minus gamma plus 1 minus V initial power minus gamma plus 1 upon this minus gamma plus 1 will become gamma minus 1 because minus sign I took inside. So by multiplying by minus we will get minus into minus gamma plus 1 will be in the denominator gamma minus 1. Final step, see we have to get this equation as the easiest one. So what we will do, this K we can say P initial V initial power gamma, that is also equal to K, and P final V final power gamma is also equal to K. We already know this. We will be using this over here and we will be having smartness. This K which is multiplied by V final, we will put that K as P final V final power gamma, and the K which is getting multiplied with V initial, we will be putting it as P initial V initial power gamma. So let us put the value. This K is multiplying, but the one smart thing I told you, put this K values, the K which is multiplying with V final as P final V final P power gamma, and the K which is multiplying by V initial, put it as P initial V initial power gamma. So let us have P final V final power gamma into V final power minus gamma plus 1 minus P initial V initial power gamma into V initial power minus gamma plus 1, the whole divided by minus gamma plus 1. So you already know this math, x power n into x power minus n plus 1 is equal to x. So here also what will happen? The gamma gamma value will cancel out in the power, and work done, we will be getting work done for adiabatic. For adiabatic reversible process, we are having work done as P final V final minus P initial V initial upon gamma minus 1. So ultimately we got the work done for adiabatic reversible process. In terms of temperature and moles also you can write it down. You can write down P final V final is equal to nRT final P initial V initial is equal to P initial V initial is equal to nRT initial. So put the values, we are getting nR delta T upon gamma minus 1. So we are having both the formulas over here, work done for reversible adiabatic process, and this is the equation we are following. PV power gamma is equal to K. PV power gamma is equal to constant. So this is only for reversible adiabatic process. You have to remember, see, if for irreversible you cannot apply this. Very important point I am telling over here. PV power gamma is equal to constant, and in place of this P you can put PV is equal to nRT. You can put PV is equal to nRT. So in place of P you can put T by, I am directly writing the proportional T by V. If you put this T by V in place of this P, you will get T V power gamma minus 1 is equal to constant. Also, in place of V, you can write down T by P. Put in this equation, you will get P power 1 minus gamma, T power gamma is equal to K. All these equations are only for reversible adiabatic, not for irreversible. Okay? They have asked this question and you have to remember this is a very important point. One question they asked over here. Let us see the question. So this is the important question I am talking about. Find the incorrect relation for irreversible adiabatic process from the following. So they are asking us incorrect relation for irreversible adiabatic process. I already told you that the three equations PV power gamma is equal to K, PV power gamma minus 1 is equal to K, and the third equation where we are having P power 1 minus gamma, P power gamma is equal to K. All these equations are only for reversible adiabatic. And they have given us these equations over here for irreversible. So all these three are incorrect statement. These are only for reversible adiabatic, not for irreversible. Okay. So all these three statements, that three equations they have given over here, all of the three are incorrect over here. So all of this will be the answer. Okay. Very important point I am telling you. See, also this type of question they are asking. 1 mole of an ideal gas CV 5 by 2R at 300 Kelvin and 5 atm is expanded adiabatically to a final pressure of 2 atm against constant external pressure. By looking at this, we already got to know this is a irreversible process. And you know, in irreversible process, always the work done is equal to minus P external delta V. See, the important point over here is in this, we can see this is an irreversible adiabatic process. So you cannot apply PV power gamma is equal to constant over here. Or TV power gamma minus 1. Many questions they are asking this irreversible adiabatic, and most of the questions I can see, I have seen this, that students apply this equation. PV power gamma is equal to constant or TV power gamma minus 1 is equal to constant. Very important point beta. Never apply this for irreversible adiabatic process. So in this question, we will not apply. If you apply, you will get the wrong answer. Simply as that. Okay. So let us see how to proceed. Over here, we can apply the first law. First law of thermodynamics. What it says? The internal energy change delta U is equal to Q plus work done. And you already know for adiabatic process, there is no heat exchange. So Q value equal to 0. Q will be equal to 0. So delta U is equal to, the Q value is 0. Delta U is equal to work done. Okay. And this work done, as I told you, for irreversible process, the work done is minus P external delta V. So you have to apply this delta U is equal to minus P external delta V to get the final temperature. So let us see how to proceed. Delta U, it is NCV delta T. We already know this. NCV delta T. So I am writing over here NCV delta T is equal to minus P external, which is equal to 2 atm into delta V. Again, I am not having the volume values. So I am writing volume final as nRT final upon P final, which is 2. Okay. Which is equal to 2 minus nRT initial upon pressure initial, which is equal to 5. So this we have to solve. Let us solve. How many moles? 1 mole. Cv is equal to 5 by 2 R, and delta T, I'm writing it down, temperature final minus temperature initial, is equal to minus 2 into moles also here 1. So R T final upon 2 minus R T initial upon 5. Over here R will get cancelled. Both LHS RH is having R, so it will get cancelled. And 5 by 2 temperature final minus temperature initial we already know. How much temperature initial is? 300 Kelvin. So I'm putting over here the temperature initial values 300 is equal to minus 2 temperature final upon 2 minus 300 upon 5. So we have to further solve it. I'm looking for some space. Many calculations are there. So let us see. This is 5T final minus 5 into minus 300 minus 1500 is equal to these two getting multiplied over here. So how much we are getting? Minus 2TF, and this 4 into this minus 4 into minus plus plus 300 into 4 divided by 5. So 5TF and 2TF, this minus 2TF will come over here. It is getting 7TF. 7 into T final will be equal to 1500 plus how much we are getting? This is nothing but 60. 60 into 4, it will be 240. So finally we are getting 7T final will be equal to 1740. So temperature final will be equal to 1740 upon 7. 1740 upon 7 will be 7 2s are 14. We are getting 334. Oh, so okay. 273 we are getting. How much we are getting? 7 2s are 14. So the remaining is 334. 7 4s are 28. So 28 gone. We are having 6 and 60. So 7 8s are 56. 248.5 we are getting. 248. Approximately 248.5 we are getting over here. So this is the temperature final value. The important point you must have learned from this is that never apply this TV power gamma minus 1, which is for reversible adiabatic process, because here we are having irreversible adiabatic process. Here we have to apply this delta U internal energy change is equal to minus P external delta V. So this is a very important question. Always remember, for the reversible adiabatic process we are having these three equations: PV power gamma minus 1, PV power gamma is equal to constant, TV power gamma minus 1 is equal to constant, and P power 1 minus gamma, T power gamma is equal to constant. All are for reversible adiabatic process, not for irreversible. For irreversible, simply apply delta U is equal to work done. Okay? Delta U is equal to work done. So this was a very important question. Let us move forward now. So this was the adiabatic process which we studied. The remaining process are isochoric process and isobaric process. They are very simple one. Isochoric process we know volume is equal to constant. So delta V, I think we should first differentiate this dV. The differentiation of any constant is always equal to 0. So work done, as we already studied, always starts from the equation minus integral PdV and here dV is equal to 0. So work done for an isochoric process we are getting over here is equal to 0. Now let us see the isobaric process. For isobaric process, the pressure is equal to constant. So here, let us start again the derivation work done minus integral PdV. Here the pressure is constant, so you can take it outside and integrate dV, V initial to V final. So work done we are getting over here is minus P and integration of dV is V initial to V final. We are getting minus P delta V as the work done. Also you can have in terms of temperature, you will get it as NR delta T. So this is the work done for isobaric process. And this is always equal to 0 for the isochoric process. The work done is always equal to 0. So these are the work done derivations that I did. Firstly for irreversible process and then after for reversible process. Important are isothermal and adiabatic. Okay. So let us move forward now. We covered the work done and now we will be studying out the first law. Already I told you because we had important question for first law. So already some part we discussed about first law of thermodynamics. The important statement. What is that important statement about the first law of thermodynamics? Energy can neither be created nor destroyed. It can be converted from one form to another form. See, I want to have that feeling that student must understand how we got the equation of the first law of thermodynamics. So I am comparing it with our day-to-day life. Here I am assuming that salary is like our heat. I am denoting by Q. That bank balance change, that is increase or decreasing bank balance, that is like internal energy change. Internal energy change. It is like internal energy change. We are denoting it by delta U, and we are having here work done. But first of all, I am talking about the work done which we see in physics, and I already told you that will be integral PdV. So what is the relation? I am comparing it with day-to-day life. See, I am comparing it with day-to-day life. For example, a person earns 2 lakh rupees. His salary is 2 lakh rupees. And in that 50,000 is getting as expenses, which is a work done. So the bank balance is increasing by 1,50,000. It is like 2 lakhs is equal to 1,50,000 plus 50,000. This is our salary, which is equal to heat denoted by Q. 1,50,000 is our change in bank balance. Bank balance change. I am writing down this bank balance change is equal to internal energy change. Internal energy change, which we are denoting it by delta U, plus this is work done of physics. Work done which is of physics integral PdV. But in chemistry we know that work done for chemistry, it is for chemistry and we are studying chemistry, so I am not writing down here chemistry. We know for us it is minus integral PdV. So what will happen if I put over here this value as integral PdV, this will come to this side. What will happen? Q is equal to delta U plus integral PdV. I am taking this integral PdV to this side. Or you can say I am having this delta U this side and all these things over that side, Q minus integral PD we are getting. And this is nothing but the work done for chemistry. So we are getting delta U is equal to Q plus, this is work done for chemistry. So this is the first law equation that we get in chemistry, that internal energy change is equal to Q plus work done. So this way I derived this equation, and I compared it with the day-to-day life, so that if by chance you get to forget it, you can recall by having this example. And one more important equation that relates enthalpy change with internal energy change is delta H is equal to delta U plus delta PV. This is also one of the important equations. Delta H is equal to delta U plus delta PV. You have to use it like delta H is equal to, this delta H is nothing but enthalpy change. This is nothing but enthalpy change. And this enthalpy change they are asking many times. Delta U plus, they have given us the PV values, the P initial, V initial, P final, V final. So how to write it down? Delta PV will be P final, V final minus P initial, V initial. So this way we have to use this equation which relates enthalpy change with the internal energy change. Okay, so these two equations are important. Delta U is equal to Q plus work done, and delta H is equal to delta U plus P final, V final minus P initial, V initial. These two equations, they are important for the first law of thermodynamics. So let us see what kind of question they are asking over here. 1 mole of a non-ideal gas undergoes a change of state from 2 atm 3 liter 95 Kelvin to 4 liter 5 atm 245 Kelvin with a change in internal energy delta U equal to 30 liter atm. Calculate the change in enthalpy. So as I told you already, delta H is equal to delta U plus P final V final minus P initial V initial. This is the equation you have to use. Delta U, they have given already. Many times they cannot give this delta U. Then you have to derive it. Here they have done it very easy. Delta U they have already provided. This is 30 liter ATM plus P final V final. P final is this, V final is this 4 into 5 minus P initial V initial. P initial is this 2 ATM and this is V initial 2 into 3. So how much we are getting? 30 liter ATM and plus 20 minus 6, 14 liter ATM. So we are getting over here 44 liter ATM as our enthalpy change. So you can see two equations are very important for us. One is this which relates enthalpy change and internal energy change, and one more, that is our basic equation which we were talking, that is delta U is equal to Q plus work done. Okay. We will be also solving questions that they ask in PYQ related to the adiabatic process. Like this question they asked PYQ. A monoatomic gas at pressure P1 and volume V1 is compressed adiabatically to 1/8 of its original volume. What is the final pressure? So this is the question of reversible adiabatic process. So we can follow over here P initial V initial power gamma is equal to K. So we can write down P final V final or gamma is equal to K. So definitely P initial V initial power gamma is equal to P final V final power gamma. This we will be using over here, and they have told us that the monoatomic gas is there. For a monoatomic gas we are having gamma is equal to pi by 3. Okay, so let us put the values over here. Pressure initial I am taking it as P1, volume initial is V1 or gamma is equal to pressure final we have to calculate, and volume they have stated us that the volume is getting changed to 1/8 V1 upon 8, the final volume will be power gamma. And the gamma value, as I told you, is equal to pi by 3. Okay, so I'm putting over here the value, the value is pi by 3. And here also, the value pi by 3. So let us calculate P1 V1 power 5 by 3 is equal to P final V1 power 5 by 3 upon 8 power 5 by 3. So V1 power 5 by 3 is getting cancelled. P1 into 8 power 5 by 3 is equal to P final. This 8 power 5 by 3. See, cube root of 8. 8 power 1 by 3 will be equal to 2. And 2 power 5. 2, 4, 8, 16, 32. So this will be 32. So 32 P1 will be the pressure final. 32 P1 will be the pressure final. Let us have our question. So the question was, as I can see, question got deleted, but we have got the answer, so we can move backward to get the question again. Yeah, this was the question. So we got the answer 32 P1. We applied the equation P initial V initial power gamma is equal to P final V final power gamma. We solved it and we got the final pressure as 32 P1. Okay. Next question. 1 mole of ideal gas is adiabatically and reversibly compressed to 1/4 of its original volume. Change in temperature of the gas if the initial temperature is 27 degrees Celsius. Over here, we have to use the equation TV power gamma minus 1 is equal to K. See, in the last question, you had PV power gamma is equal to K. Why? Because we were dealing with pressure and volume. But now we are dealing with temperature and volume. So we have to use the equation TV power gamma minus 1 is equal to constant. I am writing down T initial V initial power gamma minus 1 is equal to T final V final power gamma minus 1. Okay. Over here they have said us the gamma value is 1.66. This is nothing but 5 by 3 only. So put the value 5 by 3. T initial V initial power 5 by 3 minus 1 will be 2 by 3 is equal to T final V final power 5 by 3 minus 1 will be 2 by 3. And the temperature initial they have given us as 300. So 300 P initial power 2 by 3 is equal to temperature final into volume final. They have said the volume got 1/4. So volume initial upon 4, the whole power 2 by 3. So let us calculate this volume initial got cancelled. We are getting 300 into this 4 power 2 by 3 is equal to temperature final. So let us see what is this 4 power 2 by 3. 4 power 2 by 3. 4 square will be equal to 16. So this is 16 cube root. See, if you see 8 cube root is equal to 2 and the 27 cube root is equal to 3 and it is in between. Very important interesting thing, 8 cube root is equal to 2 and 27 cube root is equal to 3 and this 16 is in between, so it must be approximately 2.5. So let us put the value 300 into 2.5. How much we are getting? The temperature final we are getting over here is 750 Kelvin. But they have asked over here the change in temperature. You can see they have asked us the change in temperature. So they are asking us the delta T value. Delta T is nothing but temperature final minus temperature initial. We got the temperature final as 750. And the temperature initial as they have already given us 300. So how much we are getting? We are getting 450 Kelvin as our answer. We are having this 449. Of course, we will get approximately only in this type of question. We cannot get the exact value. So we got 450 Kelvin and the answer will be 449 Kelvin. Okay. So these three equations, PV power gamma is equal to K, TV power gamma minus 1 is equal to K, and P power 1 minus gamma T power gamma is equal to K. They are very useful, but only for reversible adiabatic process, not for irreversible. Okay. Very important point. So let us move towards the second law of thermodynamics. Let us have the second law of thermodynamics. The second law of thermodynamics deals with entropy. It deals with entropy. So let us first understand what is the entropy is. See, dear students, entropy is nothing but measure of randomness, disorderness. It is measure of randomness, disorderness. Okay. And the second law deals with this entropy. What it says, what is the statement of second law of thermodynamics? That the entropy of universe is increasing day by day. Or you can say the entropy is constantly increasing. Entropy of universe is increasing day by day. So I have told you that suppose this is our universe and we are having system in it. This is our system and this is our surrounding. This entropy we are denoting it by S, denoted by S, and we are talking about entropy change. So I am denoting inside the system we are having entropy change at delta S system. In the surrounding we are having entropy change at delta S surrounding, and the overall entropy change, that is the total entropy change, will be delta S universe. So what is the relation? Delta S universe will be equal to delta S system plus delta S surrounding. Delta S system plus delta S surrounding. Okay. This is total entropy change. If you say that is also equal to delta S universe. They will always say total entropy change. Total entropy change. That means they are talking about delta S universe. Okay. This is a very important line. We will be studying first of all regarding the delta S system. This is entropy change in the system. Entropy change in system. First of all, let us have focus on this entropy change in the system. Let us have calculation of this entropy change in the system. See, like work done, you calculated the small work done, and then after you integrated it to get the complete work done. Over here also, we will be having first of all calculation of small entropy change. So let us first define small entropy change, which I am denoting it as ds. That ds will be equal to dq by t. This is nothing but small entropy change, ds is equal to dq by t. And always you can see that for the second law we have to get of the help of the first law. We need the help of first law. And in first law you saw that delta u is equal to q plus work done. This delta u is nothing but NCV delta t. Q is heat exchange and work done is minus integral PdV. So if you differentiate both sides, you will get NCV dt is equal to dq, and this differentiation of integration will be cancelling the both, and you will get minus PdV. So here you can see we are getting this dq equal to ncv dt plus pdv. This is the equation we are getting over here. This is the very important equation which we will put in this ds is equal to dq by t ncv dt plus pdv the whole divided by t. This is the small entropy change. And now let us calculate the complete entropy change for the system by integrating this small entropy change ds. So we are getting this ds, integration of this ds will be integration of ncv dt plus pdv the whole divided by t. So let us see what we are getting. Delta S entropy change in the system will be equal to, let us break down this ncv dt upon t, limits t initial to t final, plus integration of p by t dv. See, we can integrate this because with dt we are having the t term. For this we have to use the ideal gas equation, pv is equal to nRT. So p by t will be equal to nr upon v, because we cannot integrate this. Along with dv we should have the v term. Okay, so this is the integration of this will be nothing but ncv ln t final upon t initial, and over here instead of p by t we are having nr by v. So nr by v, and the integration will be natural log of v, limits v initial to v final. So we are getting v final upon v initial. This is the delta S system we got. So ultimately we got the delta S system. Delta S system, we got it as ncv ln t final upon t initial plus nr ln v final upon v initial. This is for the system, and in this also we can have for reversible adiabatic, for reversible isothermal, we can calculate for specially for different processes. Let's see for isothermal. For isothermal process, we know that the temperature is equal to constant. Temperature value is constant over here. So T initial and T final are equal. If you put this T initial is T final over here, this term will be equal to 0, because natural log of 1 is equal to 0. So we will be getting delta S system, the entropy change in the system for isothermal process equal to nR ln V final upon V initial. And as I told you already, we are having Boyle's law over here for isothermal. Boyle's law says P initial V initial is equal to P initial V initial is equal to P final V final. So instead of V final upon V initial, we can have P initial upon P final. This is a PYQ question they asked. So let us see the PYQ question after this. Instead of V final upon V initial, I can put it as in terms of pressure as P initial upon P final. So we are getting nR ln P initial upon P final. This is our equation of entropy change for the system for isothermal process. nR ln V final upon V initial, and in terms of pressure nR ln P initial upon P final. So this was the question they asked in NEET. For a sample of perfect gas, when its pressure is changed isothermally from pressure initial to pressure final, the entropy change is given by. So already now only we had discussed this. Now already I told you that the entropy change delta S system for isothermal, we already saw this. It was NR ln V final upon V initial, but they didn't ask us in terms of volume. They asked this in terms of pressure. So it is P initial upon P final. So we got NR ln P initial upon P final. This B option as our answer. Okay. So you got this. This was all about second law of thermodynamics. In adiabatic process, if you see the Q value is 0. So dQ will be equal to 0, and therefore for adiabatic process the entropy change delta S will be also equal to 0. I am telling this for reversible adiabatic process. The entropy change will be equal to 0. Why? Because you already saw the definition for small entropy change, ds is equal to dq by t. In adiabatic process the dq is equal to 0. So if you put 0 here, the ds small entropy change will equal to 0. So the complete entropy change for reversible adiabatic process will always be equal to 0. For all other process you can find it out. So this was a very long session already. We are having 1 hour 15 minutes now. Already it was a 1 hour session. So hopefully you enjoyed this session. Let us meet in the next session. Thank you so much for coming. 5 students.